Welcome to Saxon Math, Lesson 116, Division by Zero. When we solve equations in algebra by reducing, we need to be really careful about one specific value, and that value is 0. When we have an expression like 3x over x, we would really commonly want to cancel out the x and the x and get 3. But we need to be really careful in mentioning that this is only true if x does not equal 0. Now, a lot of times in our math classes, we're told that we are not allowed to divide by 0 and that it breaks a lot of rules, but we're not given a lot of explanation. So today's lesson is going to try and give you some of those explanations. We're going to offer up two examples where we'll see graphically and numerically why we can't divide by 0, and then a third example where we see how we would apply this in an actual problem you might see in a class next year. So, why can't we put 0 in for x? Well, if we have 3 times 0, that's 0. And if we plug in 0 for x on the bottom, that's 0 over 0. Now, if you plug 0 over 0 into a calculator, you're going to get an error. If you ask your phone to do it, if you ask Siri or Cortana what 0 divided by 0 is, then she'll start telling you a joke about not having friends, not having cookies, sharing them, and being sad. Now, it's not a very funny joke, and it doesn't really explain why we can't divide 0 by 0. But today's lesson should. Now, before we go into that first example, I want to look at some of the values around 0. Now, here I've graphed from -1 to 1 with 0 in the middle. Now, you can see the -1 is over here, +1 is over here. Closer to 0 is -1/10, or 0.1, or +1/10. Equally far away, but much closer than 1. Even closer to 0 than 1, or 0.1, is 0.01, or -0.01. Now, in our first example, we're going to use these three values to represent approaching 0. Because I want to know, if I had 10 and I divided it by 0, what would it be? Well, with any number other than 0, if I used this set of approaching numbers, if I used a number away from it, 0.1 away from it, 0.01 away from it, I would be getting very close to what my actual answer would be. And it would be similar on this side and on this side. They would both approach the same number. Now, does this work with 0? Well, let's check. If I have 10 over -1, well, that's -10. If I have 10 divided by -0.1, well, dividing by a decimal, I'm going to need to move the decimal over and over, which would give me 100 over 1. Here I'm going to move it over twice, which would give me -1000. Now, I'm approaching a very large number, and in fact, the space between 10 and 100 is actually much smaller than the space between 100 and 1000. Here, I'm increasing by 90. Here, I'm increasing by 900. Of course, in a negative way. Now, this increasing difference is characteristic of something called exponential growth. So we can see here that our growth is getting larger in between each one, meaning we'd eventually be hitting infinity, the largest possible number. And this would eventually lead to negative infinity. Now, what about 10 over 1? Well, that's 1. 10 divided by 0.1 would be 100. And 10 divided by 0.01 would be 1000. Now, this is going to have that same exponential growth pattern leading us to positive infinity. So here I have the smallest, well, the largest negative number, which would be smaller than anything else because it's a negative quantity. The largest negative quantity and the largest positive quantity, and the same function going from different directions approaching the same number. Well, at 0, I either have all of everything or none of everything. I have absolutely the opposite of everything. Well, what does that look like if we graph it? Now, because sometimes the numbers don't quite make sense, and infinity is a little bit hard to think about. When we graph it, it would look like this. So you can see here, as we're approaching 0, these two lines move away from each other. When the negative x is approaching 0, the y value approaches the bottom of the y-axis. As the positive x value approaches 0, we approach the top of the y-axis. Now, that means these are as far apart from each other as they can be on any graph. So what's the value? We don't know. Is it the value up at the top? Is it the value up at the bottom? We can't tell. It's indeterminate, so we say it's undefined. Now, thinking graphically might be a little bit confusing, but we can take it back to some math that you probably learned around 3rd and 4th grade, which are our math, multiplication, and division facts. Now, I know that all of you learned that if we have any multiplication fact, such as 4 times 5 equals 20, it can be written as two separate division facts, where we take the product and we divide by one of the factors and have an answer be the other factor. So 4 times 5 is 20, so 20 divided by 4 is 5. 20 divided by 5 is 4. When we get into example 2 will show that if we try to make a multiplication problem with 0, this kind of breaks down. Now, if we have, for example, 2 times 0 equals 0, that's a true multiplication fact. But if we make it into two division facts, it doesn't quite work. Now, here, if we said that our product 0 over 0 equals 2, or 0 over 2 equals 0. Now, 0 divided by 2, if I split 0 between two people, each person gets nothing. That is a fact. That one makes sense. But if I split nothing amongst no one, would each non-existent person get 2? That doesn't make sense and is not a fact. And we can see this problem get even worse when we say, what if we have 3 times 0 equals 0? We can create this same division fact here, where we have the product over 0 equals 3. And now we have the same division problem equaling two different things. And you can start to see why, when we divide by 0, we can't really say that it equals anything. We can't say it equals anything in particular because it could equal anything. And we don't know which of those anythings it is, so we call it undeterminate. Now, example 3 is going to show us how we'd actually use this, because if we can't say what the solution is, how do we use it in a problem? Well, the way we use it in a problem is something called an excluded value, because if we look at this graph over here, I'm going to have my pen mark everywhere except for the y-axis. In y equals 10 over x, the number I can't use for x is x cannot be 0. But not every equation is so clean, is so simple, as having just the variable on the bottom of a division sum. So we might have something a little bit more complicated that has an excluded value. And if you're using a table of values to find your answer, you don't want to have to go through all sorts of math just to find out, I've divided by 0, and I can't use this point. So let's look at example 3. If we were asked to graph the following equation, what number could we not use for x? And the equation we're given is y equals 12 over x plus 2. And the first step is to find where is the variable. Identify the variable. X is in the denominator. Of x plus 2. Now, it will not work when the denominator is 0. In other words, when x plus 2 equals 0, it won't work. So I take that equation, x plus 2 equals 0, and I solve for x by subtracting 2 from both sides. That'll give me x equals negative 2, and this is when it won't work. If I plug in negative 2 for x, I'd get 0 on the bottom. The way we write this is x does not equal negative 2. And then we'd be able to solve it. So you might see problems asking things like this. And you might see problems saying, for this equation, what would be an excluded value? Well, the excluded value for this equation is negative 2. Negative 2 is the number we can't use for x. It's what we've excluded. It's what we've left out. Now, today's lesson is the last lesson I'm going to be asking you to do homework, and as such, I wanted to give you a small reward. You can skip problems 2, 9, 13, 14, 15, and 16 if you're in Mr. O'Loughlin's class. Skip the started problems. You're going to have a little bit of a break today. All right? Have fun, stay safe, stay inside, and wash your hands.